Can everyone hear me? Great. All right, so my talk is about this project I worked on last year and over the summer called Nebulet. The kind of subtitle here is rather kind of grandiose. I'll get through, most of the talk will be about explaining what Nebulet is, because it's more complicated than it seems, just the definition. Right, so a few disclaimers before we start. I'm not going to talk about Spectre or Meltdown. They play a big part, but I'm not going to talk about them because there's no, I didn't do any work trying to mitigate Spectre or Meltdown. In a lot of ways, they kind of destroy the idea altogether. So I'm just ignoring them, saying they don't exist. Maybe in a couple of years, there'll be hardware that doesn't have it. But I read an article that says that's actually impossible, so whatever. Also, I haven't worked on Nebulet in like 6 months. It doesn't work anymore. At some point, I'll probably go back and fix it and rewrite it. Nebulet was a large part kind of a learning project for me. I started it when I was in high school, so I was kind of learning the whole OS thing. I'm still learning the whole OS thing. So yeah, so also there's no demo because it doesn't work anymore. I wish there were a demo, there's not. All right, so to be perfectly accurate, all of the words on this slide are wrong, except Nebulet. It is called Nebulet. It's not new. This idea, this thing that Nebulet is, which I will define later, is not new. There has been other projects that have done it, and I'll talk about those too. And it's not necessarily an OS, so it is Nebulet, but that's pretty much it. This is probably the most accurate definition. A thing that does a thing that is part of a group of similar things, which is part of a group of less similar but still similar things. And I'll explain all the things in this over time, starting backwards. But before I get to that, I'm going to explain who I am. I am Lachlan Sneff. My Twitter handle is Lachlan Sneff. My GitHub handle is Lachlan Sneff. That's all the social media I have. I'm a university student. Until recently, I worked at Wasmer. If you want a job working on WebAssembly runtimes or lots of other WebAssembly stuff, talk to Cyrus and work at Wasmer. It's cool. You'll like it. I'm interested in WebAssembly, obviously OSs, runtimes, and that's like all the stuff I've worked on. All right, so to begin, I'm going to define the last term of that, the things, and it's operating systems. So operating systems, here's a definition from Wikipedia. It's an operating system is a system software that manages computer hardware and software resources and and so on. There's a lot of stuff in this sentence, and it's accurate, obviously, but there's a lot of it. So essentially, the definition I'm going to use is it makes the code you run not break your machine. And that isn't totally correct either, but it explains an important part of an operating system's job, which that an operating system makes sure each program doesn't break anything outside of its little walled garden. And this obviously doesn't always work, but it does most of the time. So that's the really important part about operating systems, and Nebulet kind of exploits this property of operating systems to potentially make it faster, other benefits, whatnot. So an important way operating systems do this is through this concept of protection rings. It's called other stuff in other architectures, but pretty much all architectures have this similar idea. And essentially, there's two rings. There's ring 3, and then there's ring 0. And so ring 3, so the kernel that, actually I got these backwards, it doesn't matter. So the kernel that is part of the OS, here, I'll bring it up here. The kernel that is part of the OS runs in ring 0. It basically orchestrates all the other programs and makes sure they don't fuck up. That's pretty much it. And so the rest of the operating system that is user mode runs in ring 3, where the kernel can keep an eye on it. So this isn't important right now, but it will be later, because a lot of Nebulet's design is based on whether this is necessary or not. All right, so we've gotten one of the definitions. They're operating systems. And so we're going to work through all of these over time through the presentation. So Nebulet is a thing that does a thing that is part of a group of similar things, which are operating systems. Great. So I'm going to talk about operating systems. Then I'm going to say there's 3 main types. There's monolithic operating systems, and this is what you normally think of when you think of an operating system. Linux is a mostly a monolithic operating system. Windows is mostly a monolithic operating system. Mac OS, FreeBSD, all that kind of stuff. They basically, I think probably a deciding factor of monolithic operating systems, what defines them, is that the driver, this is not the whole definition, but drivers are part of the kernel, or they run in ring 0 along with the kernel. And this is great because whenever the kernel wants to talk to a driver, it doesn't have to do much. There's not much work it has to do. It's very fast. But it's hard to update drivers. If a driver crashes, your OS crashes, you've got to restart your machine. That's most of the time. That's how this stuff works. But it's and here's how the ring 0 kernel runs. Drivers running ring 0. User mode is elsewhere in ring 3. And they're pretty fast, right? I mean, this is kind of the defining factor. They're simple and they're fast, but it's difficult for them to be modular while still being safe. And Linux does have a kind of modular monolithic design where you can load drivers in and out. But then again, if the driver crashes, your OS goes down. So that's the main problem with monolithic operating systems. And the other main design is a microkernel operating system. And these are less common. GNU Herd is one. I don't know if you guys have heard of that. Yeah, it's interesting, I guess. Yeah, so with these, the defining factor here is that all the drivers are in user mode, or most of the time. They're just normal processes, and they have extra access to hardware or system resources compared to like a process of a normal process. But then again, yeah, so the kernel runs in ring 0, user mode runs, all the drivers run in user mode. This is great because if a driver crashes, then your OS, you just restart the process. Like it's great. And you can just swap them in and out. It's just the main issue here is that it's modular, but it's slower because if you don't pay a lot of attention to the overhead here, whenever you want to do anything with the driver, say you want to talk to the file system, you have to go from user mode to kernel mode to user mode to kernel mode to user mode. Although, so you've got to talk to the kernel, and then the kernel talks to the driver, and then the driver talks to the kernel, and then the kernel talks back to your process. So there's a lot of overhead. You can optimize it, but kind of the simplest design of microkernel is like that. So it's a great design. Ideally, we would all be using microkernels. Ideally, we would all be using GNU Herd, but real life exists. All right, so the other design, and this is not a classic operating system, and it really doesn't fit into the other three categories either. It's a software isolated operating system, or I call it a software isolated operating system. It has many names, many forms. There's been a couple of them. Probably the best well-known one is Singularity OS. Oh dear. Yeah. Singularity OS was this Microsoft research operating system from like 2005. They wrote the entire kernel in C#, the entire user mode in C#. Everything ran in kernel mode. Super cool. A lot of Nebulet was like kind of inspired by Singularity OS. It's too bad it kind of got canceled. And it turned into Midori, but that also got canceled. So Nebulet is a software isolated operating system, so to speak. SIP space stands for software isolated process space, as opposed to user space, as it's called. And in this case, you can see that everything runs in ring 0. And this would normally be super unsafe. Like you couldn't take your regular Linux, image and run all your normal processes in kernel space. Because then each process could, mess up your machine. It could overwrite, read other processes, overwrite, read the kernel. Super bad. Don't do that. So the reason why you can do this with a software isolated kernel is because of the name, software isolation. All of the processes are in fact isolated from each other, not by hardware as in ring 0, ring 3, but by the design. They're written in some safe programming language. For example, Singularity OS used C#, and there was a safe subset of C#. And so all of the processes were required to be safe. They couldn't interfere with each other. If you're interested in Singularity OS, there's some great white papers about it. I definitely recommend it. And Nebulet is inspired, as I said, a lot by that. So yes, so the kernel, these drivers are kind of, I put them halfway in the kernel, halfway in SIP space because they're kind of both. And the great thing about this is, say your process wants to talk to the file system, all it has to do is cross from the file, from SIP space, and it can just, it's the function call essentially to talk to the driver, or maybe it's two to go from the process to the kernel to the file system, but it's a function call is like super fast, way faster than crossing between rings. So this is great. You reduce a lot of the overhead, assuming your software isolation works, it's still safe. Pretty much no downsides here, except you have to write your whole operating system, all your programs in like C#. Not a bad thing, but like if you write all of the programs in C#. Anyway, this is kind of, is it monolithic? Is it microkernel? I'd say it's microkernel, but it has kind of things from both. The drivers run in the kernel. That's monolithic, sort of. It's a microkernel because the drivers are just processes. I don't know. It's both. It has advantages as well. Syscalls, that is talking from your process to the kernel, from the process to one of your drivers, is super fast. It's just a function call. That's the best thing about this kind of thing. It's super fast. Best of both worlds, sure. So going backwards, it's a software isolated operating system. And ignore the grammar here. It doesn't matter. All right. So the next thing is a thing that does a thing. So the thing that it does is WebAssembly. It does WebAssembly. So does everyone here should know what WebAssembly is? Does everyone know what WebAssembly is? Raise your hands if you don't know what WebAssembly is. All right, cool. This is great because when we were first starting these meetups, we defined what WebAssembly was each time. And now people are, it's great that everyone knows what it is. I'll just go over it quickly. You can take your programming language, this is Rust, and you compile it to WebAssembly. So essentially, it's a ISA instruction set architecture that's defined for an abstract virtual machine. So essentially, really, basically, it's a programming language that other programming languages convert into. You don't write WebAssembly yourself unless you're a masochist. Yeah, so it's the best thing about WebAssembly is it's fast, safe, portable. Really, the only thing that matters here is it's safe. And that's the only thing that matters to Nebulet. We can run WebAssembly. It means we can run WebAssembly on its own, and it's still sandboxed and isolated from the rest of the system without having to use ring 0, ring 3, complicated virtual memory mappings like a normal operating system would. So there we go. It runs WebAssembly. It does WebAssembly. It runs WebAssembly. And so if you move the words around while cutting off the cruft, you end up with WebAssembly. Nebulet is an operating system that uses WebAssembly's primary executable format. It just means that it only runs WebAssembly. It's like on Windows, if it were like a .exe, or on Linux, it's like an ELF binary. It's just WebAssembly. It's like a WebAssembly binary. And so we don't have to worry about safely running anything else. And then once you put it all together, Nebulet is a microkernel. And this is why I said the first slide was just all wrong, because Nebulet itself is not an operating system. It's a microkernel. I don't know. It's a naming thing. Nebulet itself is just the microkernel part. There's no name for the whole operating system because I didn't write the whole operating. I just wrote the kernel. So it runs WebAssembly in ring 0 for decreased syscall overhead, and that's kind of the gist of it. This is why it exists. So that's the next slide. Why make this? And you can answer this in 3 ways. One, it was fun. It was really cool writing this. It met a lot of cool people. Just kind of get my foot in the door in this kind of the operating system stuff. It was really cool. Also, the second one is really important to think about. This design, software isolation, offers a possible future for operating systems. Not necessarily the future for operating systems, but it's something to think about. There are ways to take ideas from this, integrate them into pre-existing operating systems. Maybe the idea that maybe running everything in the kernel is a bad idea, but maybe something should be run in the kernel. Maybe something should be run in the kernel, and if they're still safe, what's the downsides? Something to think about. Also, the third thing is that I was posting these on Reddit when I was first making this. People respond in the most hilarious way possible. This is both an insult and a compliment. It's seriously impressive. I couldn't have written that if I were in that situation. This is probably my favorite one. The other one, this is definitely a compliment. I like this one too. And this is actually something I say a lot about Nebulet. It intuitively sounds like a terrible idea. You originally hear like Nebulet, like what, running WebAssembly and kernel, like the fuck? Like it doesn't make any sense. But then you think about it more and you start to realize, well, maybe this isn't necessarily a bad idea. Maybe it's a good idea. I'm not going to go that far and say it's a good idea, but maybe it's not a terrible idea. As I said before, it's something to think about for the future. Is this idea something we want to invest in integrating into operating systems? Does it provide benefits? Are the cons of doing this worth it? Yeah. Now that there are like things like Spectre and Meltdown, a lot of the advantages of this are reduced. But there's still definitely places where this idea, software isolation, running without the ring 0, ring 3, or whatever you want to call it, depending on the architecture, there are definitely places where maybe that's better. And maybe your program still needs to be safe. Maybe you still need to run untrusted code, but maybe you can do it in such a way that you don't have to worry about Spectre and Meltdown. Maybe you run your untrusted code, still WebAssembly, so it's safe, but to avoid Spectre and Meltdown, you dedicate a whole core to each process, to each untrusted process. Or maybe you have like an ARM processor that has like 1,000 cores, and you can run 1,000 untrusted processes. And so this is the kind of future, maybe, of computing where we have smaller and smaller, more and more cores, smaller and smaller CPUs, so to speak. But we still need to run, untrusted code, like edge computing, for example. Maybe if we have to worry about Spectre and Meltdown, maybe, as I said, we can dedicate a whole core. Maybe we can have thousands. I don't know. I mean, if you listen to the people from like 1995, by now we'd have like 1 billion cores per CPU. That didn't happen, but maybe in the future. Yeah. So that's it. Thank you. And are there any questions? Because there must be questions. Please. Yeah. Go ahead.
So you mentioned ring 0 and ring 3, and they are separated by hardware. Can you elaborate on that?
Sorry, what did you say?
Can you elaborate on the rings, ring 0 and ring 3? They are separated by hardware, you mentioned?
Yeah. Can you guys hear me through this? Great. Yeah, so I'll go back to that slide. Yeah. So ring 3 and ring 0, you can think of them as being separated by hardware. The CPU, when you running in, say, when the CPUs, there are essentially different modes of the CPU. When your code is running in ring 0, like with the kernel, it's a mode of the CPU where it has more access to hardware. And when it's running in ring 3, it's more kind of, it has less access. And I overly simplified it. It's not just that there are ring 0 and ring 3 that makes like modern operating systems safe. It's that this, in conjunction with the fact that you can swap out virtual memory mapping and do all sorts of stuff, provides a way of sandboxing like just regular untrusted code, each process from each other. Sorry, what was the original question?
So the question is, this separation, is it hardware or software?
It's hardware. This is you can think of it as hardware. It's direct features of the CPU that do this.
Okay, another question.
Yeah, go ahead.
Okay, so do you think that this is like an alternative to Docker? It can provide a solution similar to that?
To Docker?
Yeah, to Docker.
Oh,
Docker engine.
Yeah. Maybe it's just another. Maybe you wouldn't. I wouldn't necessarily go that far for now, but it's something you could. It's possible. It's like the same way, for example, like Cloud ABI is a solution to that. It's like a similar kind of viewpoint on that. It's not a replacement, but maybe it's underlying difference. Yeah.
Can you explain Cloud ABI real quick?
Oh yeah, Cloud ABI is it's an alternative to like POSIX sort of. It's a capabilities based like ABI that it's designed so that you can have an untrusted binary that you just like download from the internet, but you can run it without containers, without virtual machines, on your computer, and because it's capabilities based, it can't access anything that you don't tell it to say that it can access. So it's a safe alternative maybe to POSIX. I don't know if you want to think about it that way. Yeah. Cloud ABI. Cloud ABI. Yeah.
So I read about Singularity and Midori a
Yeah.
while ago, and one of the things that I thought was very interesting was the work that they had done in making the interface between processes safe on like a type level. So doing
Yes.
message typing, and the state of the channel changes with every message exchange.
Definitely, that was a really interesting part of
does your system
the whole Midori Singularity OS. WebAssembly can't do that yet. Not yet. In the future, it's going to have a more complex type system. It won't just be 4 integer type, 2 integer types and 2 float types in the future. There'll be garbage collection, references. So in the future, maybe you'll be able to do like a kind of type system and have all of your kind of your contracts, which I think was a term used by Singularity, kind of type checked at compile time or at instantiation time or something. But it doesn't do that yet. But it's a possibility.
As a quick follow-up, then, what does the process for sending a message from, or calling a function or whatever from one process to another look like in Nebulet?
In Nebulet?
Yeah.
So there's kind of essentially, I didn't go that far into designing like a kind of a system like API for like programs running on Nebulet. I essentially designed it after Fuchsia, where it has kind of message passing, but it's not like it's not like type to message. Or Fuchsia has it uses like some protocol buffer like thing to pass messages, but essentially it had like channels. You could just pass raw data between processes. But actually calling like a system call like into the kernel is literally just you're calling an imported function of the WebAssembly module. It's just calling a function. So that's very fast. Yeah.
What do you see as the lowest hanging fruit for how you can improve operating systems today, or what are you looking to do next to push this forward?
Yeah, it's an interesting question. Stuff like the fact that Linux now has like eBPF, what is it? I forget what it stands for actually. But Berkeley Packet Filter. Yeah. So you can run essentially scripts in the Linux kernel safely. It's I don't know. Is it Turing? I don't think it's Turing complete. I see. Yeah, so essentially, there are definitely, for example, if you could run WebAssembly in, say, the Linux kernel, and you could write your drivers in WebAssembly, it would kind of provide an extra level of safeness to writing drivers. It'd make it easier to swap drivers. I don't know, stuff like that. I think there's a kernel, maybe is it FreeBSD or something that runs Lua, that you can run Lua in the kernel? There's some... Oh, really? Yeah, I was saying, yeah, Berkeley Packet Filters, yeah. So there's definitely lower hanging fruit where running WebAssembly in the kernel would be a good thing. For example, there's a lot of, when you want to have like a very high throughput web server, for instance, you can, instead of just using the Linux network stack, you can move the network stack into user mode, write your own that is more tuned for like a specific use case, and you can increase throughput a lot. But maybe it'd be better, like, instead of doing that, it's extremely complicated. Maybe we could just move our program into the kernel so we don't have to worry about that kind of back and forth between the kernel and user mode wherever we're passing a packet. So maybe it'd be beneficial to say, I want this program to run really fast, like I want this web server to be really fast. Let's compile it to WebAssembly, run in the Linux kernel, passing back and forth, it's super fast. It's just pointers instead of having to copy memory over and over between the CPU modes. Maybe that'd be beneficial. Actually, there was a project called Service or something that someone actually working at Wasmer worked on a while back. That was a Linux kernel module that ran WebAssembly in the kernel. And there's also WASMJIT. I don't know if you guys have heard of that. It was a similar idea. And WASMJIT saw they were just doing a simple, like, it was a simple, like, program that just, called system calls. It was like the write system call or something a lot of the times. It was like 4 times faster than the same program running in user mode because passing between user mode and kernel mode is really slow. So there's definitely advantages. And there's lots of low-hanging fruit that you could solve by just adding a WebAssembly compiler into a kernel. I don't recommend it, but it might solve some problems.
Cool.
Yeah.
Do you think that WASI would be a good interface for an operating system like this?
Yeah, definitely. WASI would probably at least would be kind of an ideal API for this. There are definitely parts of it that it wouldn't work. Like drivers probably wouldn't necessarily use WASI API because they need to access more kind of host stuff. But definitely, if you wanted to run your regular WASM module on Nebulet, if it had a WASI implementation, it was written before WASI existed. WASI would be an ideal API. Yeah.
Do you want to explain real briefly what WASI is?
So WASI is an API based from the capability possible that you just mentioned, the capabilities model. It's a standardized API that can be implemented in a variety of different systems with different engines, and so it would be an interface for accessing, I/O, networking, content, file access, that kind of stuff.
Any more questions? Mackenzie.
And no, by the way, Dan works on WASI, so he's the expert.
Serious question, Lachlan. What happened to ring 1 and ring 2?
It's a legit question, actually. They exist, or at least they exist. What's interesting is Windows used to, maybe they still do, but they used to run where instead of having drivers run in ring 0 with the kernel, it would be your regular user mode programs run in ring 3, your drivers run in ring 2, nothing runs in ring 1, and then your kernel runs in ring 0. I don't know why they did that. Maybe it's some additional protections. They can't overwrite the kernel, though they can overwrite themselves. They exist. They're just not really used. Yeah. Yeah, exactly. The appendix of x86. Any other questions? Thank you.